Now, we come to one of the most critical definitions in the course, dimension. The dimension of a vector space is the size of a basis for it. And it's written dim v. And we define the rank of a set of vectors to just be the dimension of the span of those vectors. And we write it as rank S. So here's an example. These vectors are linearly dependent. So their rank is less than 3. This is not a basis. There must be a smaller basis. Well, in fact, 2 of those vectors will form a basis. So that shows that the rank of this set of vectors is 2. Here's another example. The vector space consisting of the span of the 0 vector is spanned by an empty set. And therefore, the rank of this set is 0. Now, for a matrix, we define the row rank of that matrix to be the rank of the rows of the matrix. And similarly, we define the column rank to be the rank of the columns. So another way of saying it is that the row rank of a matrix M is the dimension of the row space of M, written row M, and the column rank is the dimension of the col space of M. So here's an example. The rows of this matrix are the vectors we saw before, and we saw earlier that the rank of those vectors is 2. So the row rank of this matrix is 2. Now the columns are these vectors. And one of these vectors is 0. It's clearly not needed for spanning. So again, the column rank of this matrix is also 2. Here's another example. Well, this row has a non-zero entry in the first column, and none of the others have non-zeros in the first column. This row has a non-zero in the second column, and none of the others do. And this one has a non-zero in the third column, where none of the others do. So these 3 rows are linearly independent. Therefore, the row rank of M is 3. The columns are these vectors. Now, the first 3 columns are linearly independent, but you can express the 4th column as a linear combination of the other 3. So the column rank of this matrix is 3. Now, we see that in the couple of examples we've looked at, the row rank happens to equal the column rank. And we'll see later that that's not a coincidence. It's true in every matrix. Now, earlier we asked a fundamental question. How can you predict the dimensionality of the span of some vectors? So now we can answer that question. We just compute the rank of those vectors, and that gives you the dimension. Now let's look at rank in the context of graphs. Let T be the set of dark edges. Now, a basis for span of T is shown here. All right? It's linearly independent because there are no cycles, and it has the same span as the dark edges in this graph. Since this basis has size 4, the rank of T, set of dark edges in this graph, is 4. And here's another basis for the same graph. Now we see how we can use dimension to argue about the cardinality of a vector space over GF2. So now we're working with vectors over GF2. You'll remember the checksum problem. Checksum function we used was mapped an n vector to a 64 vector over GF2, where by taking dot products with 64 vectors. Let P be the original file, and let E be the transmission error. The corrupted version of the file then is written as P plus E. And what we want to know is the probability that a corrupted file has the same checksum as the original file. Well, if this error is chosen according to the uniform distribution, the probability that P plus E has the same checksum as P is the same as the probability that E is a solution to a homogeneous linear system, which is equal to the number of solutions to the homogeneous linear system divided by the number of all possible vectors E, the number of n vectors. Now we know the number of n vectors is 2 to the n, because there are n entries, each one can be 0 or 1. So in order to find this probability, we need to know the number of solutions to a homogeneous linear system. So this raises the question, how do you find the number of solutions to a homogeneous linear system over GF2? Well, the solution set to a homogeneous linear system is a vector space. So the question becomes how to find the cardinality of a vector space over GF2. Well, suppose that vector space has a basis B1 through Bn. Those are generators for the vector space. So the vector space is the set of all linear combinations of those vectors. The number of linear combinations is 2 to the n because there are n coefficients. Each one can be 0 or 1. And by the unique representation lemma, every linear combination gives a different vector in the vector space. So the number of vectors in the vector space is also 2 to the n. So this shows that the cardinality of a vector space V is 2 to the power of the dimension of V, the cardinality of the vector space. Well, it still leaves unanswered the question of how to find the dimension of the solution set of a homogeneous linear system. Now, a homogeneous linear system can be written as a matrix vector equation, AX equals 0. And the set of solutions to this is just the null space of the matrix A. So we're really asking, how can we find the dimension of the null space of a matrix A? And that question will be answered later.